Hello, and this video is going to be about both Newton's first and second laws. The reason why I'm doing both the first and the second, or actually first and second and third, talking about the second is in class, I didn't really quite get to the second law entirely with both sections. So let me just get this all settled. Boom. Okay. There we go. That is no longer fuzzy. So Newton's second law. Okay, and we said Newton's second law was basically the idea that accelerations are caused by net forces, and objects always accelerate in the direction of that net force. Okay. Now, Newton's second law goes beyond that, but that's the basic statement. We saw this when we pulled the ring out from underneath the chalk, which was in equilibrium, had a net force of 0. Then we removed the support force of the ring. Now, all of a sudden, the net force on this thing was just the force of gravity because the other force that was balancing that force went away. And because there was a net force, we saw it accelerate downwards, right? So that's the basic idea. But it goes quite a bit deeper than that. So let's start going through it. Because Newton's second law, or N2, is actually an equation, okay? Or it boils down into an equation. And this equation determines the size or magnitude of the acceleration that an object experiences. So first, if accelerations are caused by net forces, it would make sense that the acceleration is in some way, shape, or form proportional to the size of that net force. Now, we can demonstrate this pretty simply, and I'll do this in class the next time I see you. I did it for one class, but not the other. If I take a rubber band and I pull the rubber band back, the more I pull it back, the more force that rubber band can exert. The more and more I pull it back, the further I can launch things. That's because I cause a larger acceleration with greater net forces. So I'm just going to put that down here, and we will prove later in a different lab that the acceleration is in fact directly proportional to the net force. It's not just any old increasing relationship, it's specifically a direct proportion. And I'm also going to put vector signs over these because both the acceleration and net force are vectors, and that vector relationship is really important because we said that objects always accelerate in the direction of the net force. So it makes sense that whatever the direction of this is the direction of that. This mathematical statement captures that notion as well. But there's something else that affects the size of acceleration. And what could that be? Well, what that is inertia. Okay? Because this is the real meaning of inertia. We said previously that inertia, and let's come back to that, inertia was the tendency of mass to persist in its straight line, constant velocity motion. Okay, now that's just pretty much a restatement of Newton's first law, so it really doesn't tell us all that much about the concept of inertia. Newton's second law is where inertia becomes so much more important, where inertia becomes a quantifiable concept. More massive objects have more inertia. As we said before, the quantification of inertia is mass, or mass is the quantification of inertia, however you want to phrase that. So what does that mean? Well, this is where it takes on its role. This statement tells us as long as there's a net force, that object will accelerate. Doesn't matter anything else. Net force exists, it must accelerate. What Newton's second law also tells us, and I'm not going to put the vector sign around this one because this is not about vectors, because we're going to be relating acceleration to mass, that when you have net forces acting on different size masses, the change experienced by that mass is different, right? The larger the mass, the less the change in motion. Or the larger the mass, the smaller the acceleration of the object. And so what sort of relationship does that sound like? And hopefully you're saying to yourself, an inverse relationship. Because acceleration is indeed inversely proportional to mass. So larger masses, larger inertias, less acceleration. Okay? So these two statements together can be put together into one equation, right? If I take two proportionality statements, I can make them into an equality by bringing them together. So that says that acceleration is directly proportional to the ratio of the net force to the mass. And I can make that into an equality by adding a constant of proportionality. And it turns out that that constant of proportionality is 1. And so then we have this equation here that the acceleration is the ratio between the net force and the mass. And this, folks, is the mathematical statement of Newton's second law. It says anytime there's a net force, that object accelerates in direct proportion to the size of the net force and inversely to the size of the mass. Now, what does that mean about the role of inertia, about mass in this? Well, let's explore a common misconception. Let's say I have an elephant, right? You know, I mean, you don't know what my home life is like. Maybe I have an elephant at home, right? So here's my elephant, my Jumbo. Oh, that's a terrible elephant. I apologize to all elephants out there, but there's my elephant. And here I am standing behind the elephant, okay? Probably not a good place to stand, but there you have it. Now, if I were to lean up against the elephant and push, right? Push on the elephant. And I would say, well, what's going to happen to the elephant? I think you would be right to say nothing is going to happen to the elephant. But the question is, why is nothing going to happen to the elephant? So take a moment and think, stop and think, why is nothing going to happen to the elephant? Now, be honest with yourself. Most of you probably said, quote, the elephant was too heavy for my force to get it moving, or something to that description. Be honest with yourself, because this is all about being honest about our misconceptions. How many people said that? If you said that, that's a classic error with this. It's not about the elephant was too heavy, because if you look back to this expression, it's pretty clear that this elephant has a very large mass. I'll just make it as a capital M, right? Very large mass. But notice here, this equation does not allow for a very large mass to result in zero acceleration. As long as the net force is equal to anything other than 0, that elephant would accelerate. So it's not the mass of the elephant that is preventing this thing from accelerating. It must be something else. And what is that something else? That something else, hopefully you're saying to yourself, has to be another force. What force? And hopefully you're saying to yourself, friction. Really, it's not that the elephant was too heavy for my force to get it moving. It's that the force of friction canceled out my applied force. And we'll talk a lot about the force of friction later. But this is the reason why the net force here was 0. That's not about the size of the mass. That's just about the size of the frictional force. Now, I will grant that there's something about that frictional force that's related to mass, but that is a correlation, not a causation. Another popular thing that people say is that my force was too small to overcome the inertia of the elephant. Once again, this is in error. That's why it's in red. You cannot overcome inertia. Inertia is just this denominator. If F net is anything other than 0, this object accelerates. Okay, so here, if we draw a free body diagram, I've got I've got my force of the floor on the elephant. I've got the force of gravity. I've got my applied force forward, right? And if that's the only thing, if there were no friction, believe it or not, that elephant would accelerate. But looking at this equation, that acceleration would be really small because the effect of inertia in this case was to minimize or make the acceleration smaller than it would be if the mass were larger. Not that to stop the acceleration, but to affect its size, okay? So going back to this sentence, my force was too small to overcome the inertia. No, here in this place, I would say the friction. You can overcome friction. You can't overcome inertia, all right? And so this brings us back into, well, what is inertia really? Well, inertia, rather than saying something like a resistance to change in motion, which is what we kind of talked about, is a mass's capacity to, and the verb here is moderate the effect of net forces. Okay? To moderate, to affect the size of, not to affect the existence of. Okay? And another key sentence, therefore, is inertia cannot prevent an object from accelerating. It only affects the size of that acceleration. Okay? Meaning, small massed objects, it's very easy to change their motion. Large mass objects, it's very difficult to change their motion. But if there's a net force, the motion of that object must change, has to change. That's what Newton's second law is about. And because our brains don't think in terms of net force, because all you see when I push on an elephant is me applying a force, you don't really kind of see friction. In fact, that was Aristotle's mistake with impetus. He didn't really see friction and therefore was like, oh, okay, well, I guess that's not a thing. Okay, impetus is actually the opposite of inertia as a concept. So that is Newton's second law. Now, a couple of other additional things with Newton's second law. A equals F net over mass. Okay. Normally, though, we write this as F net equals MA, even though this is the proper way to think about it because this is the appropriate causation. We tend to write this, why? Well, we don't like denominators. That's pretty much what it comes down to for this. But the reason I want to do this is because I want to talk about units for a second. The units of the net force are going to be equal to the units of mass times the units of acceleration. So the unit of mass is the kilogram. The unit of acceleration is a meter per second squared. And so there we go. A kilogram meter per second squared. Those are the units of force. Kilogram per meter per second squared is awkward to say. Notice it's kilogram meter per second squared, not kilogram per meter per second squared. No. There's no division here. Kilogram meter per second squared happens so often in physics, we give it its own name. We call it the Newton. A Newton is a kilogram meter per second squared, and we use a capital N as its symbol. So that is the definition of a Newton, is a kilogram meter per second squared. Okay. Now, another thing about this equation, let's say I have a bunch of forces, right? I don't know, maybe there's a 5 Newton force acting in this direction, a 7 Newton force acting in this direction, an 8 Newton force acting in this direction, and a 2 Newton force acting in that direction. And I wanted to know the net force on this. Well, we go back to our earlier vector stuff. What was the most important thing when we were doing our earlier vector stuff? Hopefully what you're remembering is that we have to separately deal with each of the axes, okay? Here, when we talk about Newton's second law, I can write Newton's second law separately for each of my axes. Now, even though there's really only one net force that's the resultant of each of these, that is not, for practical purposes, good for problem solving. And so I can separately talk about the net force in the x direction, the net force in the y direction. And if I wanted the net force, I would then have to do the vector sum of these two perpendicular vectors. But this idea that I can deal with the x separately than the y, because think about that. This hopefully makes sense, right? If I push you to the left, you don't move downwards. If I lift you upwards, you don't move to the right. Forces along the vertical affect accelerations along the vertical. Forces along the horizontal affect accelerations along the horizontal. That's why in this case, with the elephant, we couldn't say it's too heavy, because the force of gravity here acts vertically, could never cancel out in a vector sense my horizontal force, right? So in this particular example, my net force in the y direction, if I said, say for example, up was positive, that would be a positive 5 newtons plus a negative 8 newtons. And in the x direction here, if I say to the right is positive, it'd be a positive 7 newtons plus a negative 2 newtons. And so I could find out separately what the net force in each dimension is, right? This idea that I can separate not that I can, that I must separate the dimensions, is something called the independence of dimension. And it is critical for our understanding of problem solving, as we're going to see. Okay.